So let's talk about the bearing selection procedure today. Okay, just a quick review. What we learned, we had the introduction of yes.
There's a buzzing in the.
Oh. There. So we had an introduction of bearings in the previous lecture, and we look at that basically the so-called bearing load and life equation. Okay. So this is the basically the bearing load and life equation, and the symbols used here: C10, L10. They're from the catalog. So C10 is called the basic load rating, okay, or basic dynamic load, and this is basically from the catalog. L10 is the L10 Life from a different manufacturer. It's slightly different, but mostly they use 10 to the power of 10, 10 to the power 6. For L10, okay, so and FD, LD, and they are going to be your desired radial load, and LD is the desired life. Okay, so this is in terms of cycle right here. So sometimes what you're giving here is probably in terms of basically not number of cycles, probably giving in terms of hours. Okay, so if you in terms of hour, and also there is this desired speed. So this guy here is hours, and this guy here is desired speed. Okay, basically it's a revolute per minute. Okay, so then you use just a slightly different equation at here. Okay, yeah. But this whole bunch at here is still 10 to the power 6, so that's your L10, right? Yeah. Okay. So in terms of using this equation at here, there are different ways of using this equation. You can always solve for one of the variable if we're given any other variables. So this is probably 10 to the power 6 you always use. FD and this one here you probably given, so then you can solve for C10, or you can solve for FD in terms of other variables, right? Okay, so. But you also need to bear in mind is what's using it here. This is basically, if you remember, this is L10, right? So this is basically 90% reliability. Okay, reliability. So this is 90% reliability here. Okay, so if you have a different situation other than 90% reliability, then you might need to actually modify this equation slightly. So for example, let's see if you're designing for selecting a bearing not really for 90, maybe 95 or 99%, so then we're going to basically remodify this equation slightly here. Okay, so what we do is we do this. There are two different ways of dealing with this different reliability. There's one way is from the textbook, okay, and there's another way is from Skf Catalog, okay, yeah. So what I recommend is we're going to use the Skf Catalog Equation, okay. So I did some comparison. They are pretty close to each other results, okay. So, but first of all, okay, this one talking about the desired life here. Then sometimes you probably wonder, so what should I pick for the desired life? Yes.
Sorry, can you go up for a second?
Okay.
For A, is that supposed to be 10 over 3 for
Oh yeah, sorry, yeah, 10 over 3. Yeah, 3 over 10. Just a second. 10 over 3, yes. Okay, good. So here's a recommended life basically from our table 11-4. For different kind of application, it recommend what's the life for your bearing, right? Okay, so you can use this table as a reference, basically recommended life. Okay, yeah. Okay, so now it's that what I just said there regarding how do we deal with the how do we deal with different reliability at here, okay? So I'm going to recommend this Skf, okay, Life Equation. So Skf Life Equation here. So Skf Life Equation is this. I'll write down the equation first, okay, and then I'll go back to this figure at here. So if I'm supposed to calculate how many lives that I have, so I have a two kind of equation here. I can use this equation. So C over Ka. That's not K. Well, let me write down this one here. I'll deal with the K anyway. Okay, or C10 equal to Ka, Fe, L over Kr, and 1 over A. So this two equation is basically, if I get rid of this Kr, Ka, you see that, right? That's basically the same equation as I written down at the bearing load life equation, just different ways of writing it, right? But as I said, I mean, you may have a different reliability. So if you have a different reliability, let's say 95%, then we're going to incorporate a reliability factor Kr into that equation. So this is the Kr at here. Okay, and the value of the Kr can be taken. This is basically from the Skf catalog. Can be taken from either this figure or from this table at here. Okay, so if you're selecting in terms of 95%, then the Kr is 0.62. So you see this time you don't call it L10 anymore. You basically call it L5, right? So that's 5% of a failure, right? A group of among that group. So that's the Kr over here, right? Yeah. Now Fe at here, this Fe is basically this Fd over here. Okay, this Fd. Now I'm calling Fe is more of just in terms of the textbook notation here. So here's a formula for Fe at here. Okay. Fe equal to V times R. R is the radial load. Okay. This doesn't. Why doesn't? Okay, good. So R is the radial load, and V taking two numbers, 1.0 for inner ring rotate, and 1.2 if it's outer ring rotates. So basically, if the application of this bearing and a shaft, right, mostly it's inner ring, and your shaft and the inner ring rotate at the same time, and the outer ring is fixed, and you take the V as 1.0. Okay, otherwise you take the V as 1.2. So that's your Fe at here. So this R is just the radial load that you calculated or from the free body diagram. Okay, yeah. So that's Fe. So we call this Fe often in time. Actually, next when we look at the combine here, we call this we basically call it a radial. We call it equivalent load often in time. Okay, we call it equivalent load here. Okay, so this one here, I think I should be more specific. I shouldn't introduce this one yet because I have two different cases. You know what? Maybe I should just write down another one here. Maybe just start this one here. This is the first case. Okay, first case. First case. Let's consider radial load only. Okay, radial load only. So you have a shaft, you have a bearing, and the loading condition at the bearing is the radial load only, which means there is no thrust load or axial load. Okay, so if you're selecting as a spur gear, there's no radial load or thrust load. Right? Sorry, there's no axial load or thrust load. There's only radial load. Okay, so that's what I mean here. So radial load only. If it's a radial load only, then this Fe will be calculated, okay, using this formula, V times R. Okay. Yeah. Okay. So how about this Ka at here? Ka at here. Okay. So Ka is another modification factor. And K is called loading factor here. And this one here, basically you take that from table 11-5. Okay. So Ka is called loading factor. Okay. Taking from this table here. So basically you have a different kind of loading condition for the application. Whether you have a light impact, no impact, or moderate impact, okay, and you pick a loading factor from this table, okay, yeah. Typically, in our application, we'll just assume it is 1, okay, if nothing really serious happens, okay, so we'll just pick it as 1 here for this Ka, okay. Is that okay? So now let's look at the first case, okay. And we'll basically look at the procedure of selecting the bearing based on this case here. When you have radial load only, so if you use a spur gear, that's probably what you're going to use. The procedures what you're going to use. All right. Yeah. So let's look at the first case, and we'll look at it through an example right here. Okay. What's the procedure for picking the bearing when you have a radial load only? Okay, so bearing selection, okay, for radial load only. Okay. Yeah. So here's the loading condition. So let's say you have a shaft, okay, and it's supported by a pair of bearing. At 2 ends. Okay, so let's say suppose that the bearing, if you look at it from this side of view here, so you have a bearing basically, okay, there's inner ring and there's outer ring, okay, and there's a whole bunch of balls, okay, inside the bearing. Okay. So let's say, suppose the loading condition is you have, okay, 2 directions of force, so that's pretty common, right? 2 planes of loading. Okay, so there's this plane and that plane. So let's say we call this is Ry and this is Rz, right? So if you look at from this direction and here, so that's what we see, right? So this is Z here. So this is Ry, this is Rz. Okay, two plane loading, right? And altogether, right, these 2 planes together you have one combined radial load. So let's call this is R total. Okay. Okay. Yeah. So that's the typical loading condition. Now you may have a different, basically Ry, Rz at the left side and the right side, right? You may have a different values. So suppose that you have a loading condition and we calculate it and we get to the following value here. Okay, so we get let's say this is the right side, Ry, the right side y equal to this much Newton, okay, and Rz, okay, equal to, okay, this much Newton. Okay, so this is the right side, and the left side Ly, okay, equal to this much, and Lz is this. Okay. Yeah. So let's say this is the results of the supporting force on 2 sides of the bearing there. Okay. So then when we design, okay, when we pick the bearing, let's say the other condition is this shaft. Let's say you have already designed the shaft, and based on the loading condition, so you find that the shaft has, okay, or needs a minimum, okay, diameter equal to 2, okay, centimeter. Okay, so you find that shaft needs this much diameter here, and your you are required to select a bearing or shaft with a desired life n equal to 100 million cycles. Okay, so here's the loading condition for the bearing, and here's the shaft minimum diameter, and here is the desired life. Right. So now let's pick a proper bearing, right, under these conditions set here. So what that means, it basically means the bearing needs to satisfy a certain loading condition. The bearing, the ball size, right, needs to have a minimum 2 centimeter, and the bearing has to satisfy this desired life right here. Okay, so that's basically what we want. Reliability, let's say at this stage we assume the KR, right, is 1.0, so we're selecting for the 90% reliability. Okay, yeah. Loading condition, let's say we select 1.0, so ideal loading condition. Okay, yeah. So okay, so what do we do from then is, if we look at our equation in here, basically we're going to make use of this equation in this case, because we're going to pick a bearing, right? So we're going to pick a bearing whose basic loading load rating, or basic dynamic load rating, say 10, right, needs to satisfy the desired value. So what we're going to do is we're going to calculate what's the C required here. So we can call this guy here as a C required. Then we pick bearings C10 that meet this minimum value C required. Okay. So then in order to calculate that value, so we have to calculate the loading condition, right? We have to calculate the R. So there are two sides here. So if I look at the right side, okay, then the total radial load is the square root of RRY square plus this RRZ square. Okay, so that's your total radial load on the right side. You calculate this, you get this much. Okay, 646.4. And then you calculate the left side. RLZ. And you get 669.9 Newton. Okay, 0.9 Newton. So basically, the left side is slightly bigger than the right side. Okay, so then what we do is we pick, if we decided to pick same bearing on both sides of this shaft, so we pick basically the higher value, the load here for our selection here, right? Yeah. So basically we said, okay, our desired load, okay, let's see here, we call it FD here, so I'll pick 669.9 Newton. Okay, yeah. Yeah. And this is the inner ring rotation. So the equivalent, basically, the FE is just basically the same as this value here. Okay, so okay, yeah. All right. So once we get this now, then we can calculate what is the required, right? So what's the required dynamic load rating? Okay, say 10. So let's say we call that C required at this stage. Okay, C required. So C required using that formula, okay, is basically FE, right, and times the desired life on the top. So desired life is LD, okay, and over the L10 at the bottom there, okay, and then 1/3. Okay, 1/3, because this is ball bearing. So if we decide to take a ball bearing, so A equal to 1/3. Okay, yeah. So L10 is the desired life. L10 is the catalog rated life, LD is desired life, so this is a 10 to the power 6. So plugging all the numbers, so this number, okay, so we're supposed to put this number here and put all the number there. But the catalog we're gonna pick, I'm gonna use is from NSK. So the catalog doesn't give me the Satan value. The catalog give me in terms of the catalog is a pound force. So before I use the catalog, I need to convert it into the pound force. So I might as well just convert this value at this stage from Newton to pound force at here. All right. So for this value at here, if I convert it to pound force, and it's approximately 150.6 pound force. Okay. Yeah. So we'll plug this 150.6 over here. And LD is 100 million life, right? 100, so the 100 times 10 to the power 6. L10 is 10 to the power 6. So that's the formula, right? All the numbers. You do the calculation, and this number turned out to be 699.5 pound force. Okay. Okay, so now it's time for us to go into the catalog to pick a proper bearing now, right? Yeah. So let's say I decided to do this, right? So we're going to use, let's see, we're going to use NSK, 6300 series. So you do have many options actually. If you don't want to use this series, that's fine, yeah. But if I decided to use this one here, so let's take a look at this series here. Okay, so this is part of the diagram from the catalog. So 603 series here. This column here gives you is the ball size of the bearing. Okay, yeah. So first, what you need to do is actually what? You need to look at what's the minimum shaft requirement. And the shaft requirement, as we said, is how much? 2 centimeter, right? 2 centimeters. So you look at this one here. This is basically the minimum here. 6304 is the one has a minimum basically shaft size, ball size, 20 millimeter. Okay. So then you go to the next figure. Okay. Part of there is basically you look at the 6304. What is the C10 value, right? They don't call it C10, they call it CR. So CR, you look at the CR here is what? 3,580 pound force, right? And that's more than what we just calculated. Our required is 600 something, and this is 3,000. So this is basically good, right? Yeah, this is good. Okay. So you can basically make a decision saying we can pick 6304, right, as our selection at here. Okay, so basically 6304, right, give us a C10 equal to 3,580, okay, which is greater than this is C required. Okay, yeah. So, and you can check mark there, and you said that's okay. Is that okay? Yeah. So that's basically actually pretty straightforward in terms of the radial load only, okay, for selecting a bearing. Any questions? All good? So now let's look at another case study here now, okay? Basically, if you're designing for a combined load condition. So that's case number 2. Okay, so for selecting bearing for combined loading. Combined loading meaning you have axial load, okay, or thrust load, and radial load. Okay, so these two together. Okay, so let's say if I draw a diagram in here, so if this is a bearing and here, this is a shaft, okay, and then you have bearings over here, okay, then the combined load basically means you have, okay, an FR at here, then you have also a FA, so that's a thrust force, and together, right, you have this combined load, something like this. Okay, there's certain angles between, but it really doesn't matter. Okay, yeah. So, but if I look back at our load and life equation, and that load and life equation is for radial load only. Basically, when you do the experiment, it's subject the bearing to the radial load only, and then you construct the bearing load and life, the curve, and you find that the equation, right? So we can use that equation basically directly on this case study here. But what we can do is maybe we can find basically equivalent, okay, this situation here to basically a radial load only situation. So essentially you have the same shaft, okay, then maybe we can find okay, a radial load only situation here. So what it means is this is a combined load, but if I can find find this equivalent case, the shaft is subject to a radial load only, and this radial load Fe will cause the same damage, okay, as this combined load. So see what I'm saying? So this Fe at here is called equivalent radial load. Okay, so this equivalent radial load essentially will cause same damage, okay, as Fa and Fr. Okay, yeah. Then we can make use of that load and life equation, right, for bearing selection. Okay, yeah. So the question is, how can we calculate an equivalent Fe based on this Fa and Fr, right? Yeah, that's the idea. So how do we calculate? Here is the formula, okay, based on not really theoretical, but based on I think it's empirical equations here. So Fe equal to Xi times V times Fr plus Yi times Fa. Okay, so that's your Fe calculation. So let's explain each one of the symbols that are here. Okay, yeah. Okay, so first of all, we know what Fa and F are, right? So they are basically radial load and axial load. Okay, and Xi at here, okay, this is called radial load factor. Because it's the factor applied to Fr. And Yi at here is called axial load or thrust load factor. Okay, because it's applied to the Fa. Okay, and there's a subscript I, so I'm going to talk about I here shortly. Okay, and V at here, V is the same idea as that previous case. So V equal to 1 for inner ring rotation. Okay, and V equal to 1.2 and for outer ring and rotation. Okay, yeah. So then the I at here, okay, the I value, okay, it takes two different values. I will take value as 1, okay, when this ratio is less than a number called e. Okay, so I'll show you what they are. Okay, so I will take a value as 1 because we're going to make use of a table here. Okay, so just remember I will take the value as 1 if this ratio is less than e, and I will take the value as 2 when this ratio, same ratio, is greater than e. Okay, e is called the limiting factor. Okay, yeah. So E is called a limiting factor for bearing load ratio. So maybe I'll write it down here. So E is called limiting factor for bearing load ratio. Okay. So as you're gonna see that, so if I'll show you the table, once we finish writing this one here. So that's all basically all the symbols that involve right here. Okay, that's all the same symbols involved here. Okay, so this is the table 11-1. Okay, table 11-1. Okay. You done with the writing here? Okay, yeah. So I'll move up the table here. So this is the table. So if you look at this table here, this is basically all the selection procedures are based on this table. So first column is FA over C naught, and second column is E, and then you have this X1, Y1, basically that's when I equal to 1, right? So this is when I equal to 1, this is when I equal to 2, right? Okay? And that I equal to 1 and 2 depends on the comparison between this and this. So now if you look at the E at here, E is a value actually depends on this ratio, FA over C naught. So basically this E is a function of this FA over C naught. Okay? So different ratio FA over C naught, you get a E value here. FA is the axial load. C naught is called static. It's called a static load. Okay, so it's in the catalog. Remember, in this catalog here, there's a C10 and the other column. This is the C naught. That's the static basic loading. Okay, yeah. So static one basically is when the bearing is rotating at a very low speed or just static, right? And this is the C naught value. Okay, yeah. So apparently, what you need to focus on is, right, E is a function of this, right? But then what we're doing is we're just remember we're calculating that equivalent FE, right? Equivalent FE here. Okay, yeah. So if I look at this FE at here, right? If you look at this FE depends on what? Depends on the FR, FA, V, and also depends on the XI and the YI value. Okay. But then XI, YI value depends on this ratio here. So basically you don't know whether you should pick I equal to 1 or I equal to 2. Right? Only when what? Only when you know the value of E. But if you want to know the value of the E, and you have to know what? You have to know the value of C naught. And if you want to know the value of C naught, and you have to have the bearing. But we don't have the bearing at the beginning. Right? So you have basically a starting point which is nowhere. So then what do we do then? So then what we do is we can, if we don't know where do we start, then we can just start anywhere between. Okay? So that's the idea. But then you have to use an iterative process, right? So you have to assume your first starting point is not an accurate one, right? And after the first step, iteration, then you go back and do another iteration. Okay, so that's basically the idea. Ultimately, you converge to the right decision. All right, so that's the point. Then I'll use an example here to show you how to go over this. There are actually different, really different ways of doing this right here. Okay, yeah. So let's look at an example, and then we'll be very clear. I'll give you an Excel actually to automate this iterating process for combined load. All right, but there are some there are some steps that you need to basically manually determine. Okay, so let's say in this example, I'm gonna select a single row deep ball bearing. Okay, and we're gonna pick the bearing based on the loading condition, and here is radial load FA, radial load FR is 1850 pound-force, and FA is 675. Okay. Shaft is rotating at this much RPM. We want a design life is 20,000 hours. Okay. Shaft has a minimum diameter is 3.1 inch. Okay. So assume that Ka is 1 and Kr is also 1. Okay, reliability of 0.9%, 90%. Okay, so that should be enough for all the numbers we need. Okay, so then let's pick a bearing, right? We're still going to use the Skf catalog there for a ball bearing. So here's the steps. Step number 1. Okay, as I said, if we don't know where to start, then you can throw a dart, right? Let's say, actually I'm starting right here. Okay, so I'm going to start from 1.55. You may not really 1.55. You can actually, I said, maybe 1.50, right? Now, however, you do have a choice. You may insist, I want to start from the 1.0. So that'll work too, actually. Okay, yeah. There are pros and cons. Okay, and depends on where you start. So we'll start this Y2 with 1.5 in my case right here. Okay. Start with the Y2 at here. Essentially, okay, what we're doing is, if you look at this X, in this case X2, Y2, both are not 0, right? But in this case here, Y1 is 0. So if Y1 is 0, let's go back over here. If Y1 is 0, what does that mean? So the equivalent load equal to just this much here, right? And that's actually the same as the case 1, right? So basically, you're considering the axial load is small and negligible, right? So, but in this case, I'm assuming it's not. But in some cases, actually, it is, right? But in this case, the number, what's the number here? The number is 675 compared to 1850. So chances are you can't neglect that, right? So that's why we start with Y2, a non-zero here. So then step number 2. Okay. So once you have the Y2 now, then you will be able to calculate the equivalent load Fe. So equivalent Fe equal to X2 times V times Fr plus Y2 Fa. So V linearly rotate, that's going to be 1. And X2 is 0.56. So you look at the table here. So X2 is always constant, right? Always constant. Okay. So times 1 times Fr, and Fr is 1850. Y2 is this number we started. Okay, 675 for Fa. So altogether you get 2049 pound-force. Okay. So that's the equivalent load based on the random selection of Y2. Step 3. Once you get this equivalent Fe, then we can calculate what is the C required, right? So basically that's the value we're going to use for selecting the bearing. So C required is equal to the Fe, okay, times, okay, numerator is the desired number of life, and denominator is the L10, or 10 to the power 6. So desired one has 20,000 hours, has this much velocity, and then times 60 minutes. You can convert that into cycles or revolutions, and then to the power of 1/3. Okay, 1/3. So that's your C required, and turn out to be this much, 22,812 pound-force. Okay, so then time to look up into the catalog now. So from the catalog, let's say using the same catalog NSK, I'm still trying to use, let's say, 63 series, 6300 series here. So here is the snapshot of that catalog. Okay. So what are we picking? We're picking a bearing with a minimum ball size 3.1 inch, right? 3.1 inch. So let's say 3.1 inch. You go down here. So the first one satisfied 3.1 inch is which one? 6316 series, right? Yeah. And that one is 6.1415, so this is slightly bigger, so that's fine. So you can basically bump up your shaft to this number here. Okay? Yeah. So let's say our first decision is 6316. So then we look at this, we said, okay, so 6316, right? This is the first decision. And this one here, if you look at this one here, then what is the C required and what is the C not? C required is right here. C required is 27,600. And this number is actually what? Bigger than what we just calculated, right? Our calculus C required. We're going to also need this one here, so we need to write down both of these here, okay? Yeah. So C 6316 has a C10 equal to 27,600, and that is greater than this C required. Okay, so this is okay. Okay, yeah. Okay, so looks like we're pretty lucky at here. You know, the first iteration, things working out fine here. And for the same bearing for 6316. So now time to go back to the loop, okay, to do some verifications. Okay, so we need to calculate exactly what is the C, what is the E value, so we can go back to the table. C naught, the static loading rating is 19,500 pound-force. Okay, the C naught. Okay, you get this guy here. Okay. So then, why do I need the C naught? Because I need to know what will be the E value, right? Because the E value can only be determined when you have a bearing selected. And the E value depends on FA over C naught. So once I have a C naught, I can calculate the ratio of FA over C naught. So calculate this FA over C naught, and this one give us 0.0346. Okay, so this give us this. Okay, so step 7. Okay, step 7, find this E value. Okay, find the E value. So look at this. If I look at this this table here, 0.346, 0.346. There's nothing there, but it's between these two here, right? Between this. So chances are you need a linear interpolation if you really need it, but this is actually just 0.22 to 0.24. Take a guess, which is what? Yeah. So okay, so that would be your E value. Okay, yeah. And this is the E value. Then what do? We have to basically compare the E value with this ratio here, right? With the ratio FA over VFR. So then we can exactly know whether we are in this column I equal to 1 or in this column I equal to 2. Okay, so let's calculate this ratio and compare to E. And that ratio is this is step 8. So this ratio is FA over FR. The V is 1, so I can just neglect that V. So this ratio is 0.36. Okay, this point ratio 0.36. Apparently, it's greater than 0.23, right? 0.23. Okay, and if this ratio is greater than E, so we are going to pick that, right? That means the I equal to 2, right? The column. So our initial starting point, it makes sense, right? Basically based on this one here. Okay. So then step number 9, okay? Then we need to know what exactly is the y2, right? y2 equal to what? Okay, not the random selection, right? So y2, if you look at the y2 here, y2 ultimately is still a function of fa over c naught, right? y2. So let's say in this case here, what would be the y2? We have 0.028 with 0.0. Well, let me write down here. Okay, yeah. Okay, so this is fa over c naught, and this is 0.28 from the table, 0.042 from the table, and this is y2. Here's 1.99 from the table. Here's 1.85, and our ratio here is 0.346, and we need to know what does this y2 correspond to, right? What exactly the value of y2? So what do? We can use the linear interpolation in here to find the y2, okay? Because essentially you have all the numbers here, okay? So find y2 here, okay? Yeah, find the y2. y2 can be found, which is 1.924. Okay, that's y2. Okay, so once we find a y2 now, okay, so here's the linear interpolation formula. So y equal to ya plus x minus xa over yb minus ya. xb minus xa. Okay. So last step. Okay, you recalculate. Okay, so recompute this fe. So here's the exact y2 based on a certain selection of bearing. So then this fe equivalent load equal to x2 times v times fr times y2 times fa, and turn out to be this much. And then you calculate again what's the actual C required now. So this C required is this much now. So same LD, okay, same L10, and this is 25,985 pounds force. Okay, C required. So this number you compare to the bearing that you picked. Now guess what? It's still less than the C10, right? It's still less than the C10. So then you can settle down on this last step, saying, okay, so the bearing that we just picked, 6316, is good. All right? But if this number you calculate is greater than 27,600, okay, then what do? Instead of 6316, you go up one notch, right? And you redo these steps again. That make sense? Yeah. So usually, it doesn't take you more than maybe 2 or 3 steps. You should converge, right? Yeah. Okay. So I have only one little portion in here to finish the bearing, and then we'll move on to the next topic. Okay. Any questions? Okay.
Yeah, that chart shows certain